Hello all, in this video we are going to see about split and merge segmentation. Often a single threshold is not enough for segmenting a grayscale image because lighting texture can vary across the regions. So in split and merge we are going to see two concepts. One is splitting, another one is merging. Splitting involves recursively breaking down the entire images into smaller pieces based on the region statistics. So we'll split until the region is statistically homogeneous. So the inverse process of splitting is merging. Will combine the similar regions into the larger one, where the individual pixels or small regions are combined in a hierarchical manner to form the large segments. So if the statistics are similar, we'll merge them. And combination of both is known as hybrid. We will start with medium grain segmentation. In image pyramid, we have seen the fine detail as well as coarse details. So the fine details mean the lower part of the pyramid. Hope you remember it. So this is image pyramid. The large part, the lower part of the pyramid represents fine detail, and the upper part represents a coarse detail, and the mid is known as a medium grain segmentation. We'll start with a medium grain segmentation, and I can either follow split or merge, depends on the image. The important algorithm we are going to see in split and merge is watershed algorithm. So watershed algorithm, first let us see an analogy. If imagine we have a high peak mountains, we have a high peak mountains, and if there is a rainfall, then the water will fall down from the mountain and it will become a valley, right? So become the valley, and imagine if you don't want to merge the two regions. So here also we may have certain valley, and the water comes along this way. If you don't want to merge, means we will build a high wall or dam to protect the merging. Okay, so this concept is an inspiration to propose this algorithm. The watershed algorithm is a segmentation technique that operates on a grayscale image, interpreting it as a high field or landscape. So this, imagine the high field of the mountain is represented as high field here. So the core idea is to find the catchment basins. So this part is known as a catchment basin, which regions or where the rain would flow into the same lake. So in this algorithm, starts with flooding the landscape from its local minima. Local minima is the point where the all the waters will accumulate. Okay, the location where all the waters will accumulate is known as local minima. As the water rises, ridges are formed. When the level of the rain is increased, the level of the water will also be increased. So where the different flooded regions meet. So this is the different flooded region. And these ridges define the boundaries of the segment. So if you don't want to build a if you don't want to merge them into a single one, means we'll build a dam to divide them. So that is known as the boundaries of segments. Now, let us see an example, mathematical example, how this watershed algorithm is implemented in image processing. So I am going to take a pixel values of 60, 30, 20, 40, 25, and 35, and these are the pixel indices. And the local minima here is 20. Local minima means both the neighboring values are high when compared to the current pixel. So consider this value, we don't have any neighbor here, and here we have 30. So this is not local minimum. Consider 30, we have 60 as a neighbor. Consider 20, 30 and 40 both are high. So 20 is a local minimum. In case of 40, 40 is high, the neighbors are very small. In 25, 40 and 35 are both high. So 25 is a local minimum. 70, the neighbor is also small. So this is a local minimum, which means 60, 30, 40, 35, 70 are mountain peaks. This 20, 25 is known as a valley because the water will always flow down to the lowest part. Mountain is a high peak. If the rain falls, then if the rain water comes down to the steep part, right? Slope, where we have steep slope. So pixel 3 value 20 is a local minimum, and pixel 5 value 25 is again a local minimum. So we have two regions, two valley regions, that is known as a catchment basin. First region is pixel 1, 2, 3, and the second region is 4, 5, 6. And this 4 is a dam or ridge we have divided. This is the boundary line. The boundary pixel is 4. So all the entire image is now divided into two regions or two segments, and the 4 is the pixel 4 is the boundary of both the regions. And application here is watershed segmentation is typically applied not to raw images but to the smoothed version of the gradient magnitude images. We can't directly apply this into the raw image. After applying gradient smoothing, we can process this. This is because images rarely have naturally occurring dark regions separated by right and ridge. So here we are completely focusing on dark values as well as light values. The lower pixels is considered as a uh, dark values, and the higher pixel is considered as a bright values. And if we are processing without smoothing, then all the pixels will have different ranges. So we need to apply this after applying only the smoothing. Challenge here is over segmentation is possible. This is a major challenge we have to address. So you see this where we can see a local over segmentation. So we have so and so pixels 60, 45, 30, 35. We are going to find the local minimum. 60 is not a local minimum, 45 is not a local minimum, 30, yes, 30 is a local minimum, 35 and 45 are high, so I am going to take the local minimum 30. Consider 25, both 35 and 45, sorry, 40 is high, so pixel 5 is local minimum, pixel 40 is not local, pixel 28 is again a local minimum, 38 is not, 70 is not. So we have three local minimums, pixel 3, pixel 5 and pixel 7. Three segmentations are possible here, but actually the required segmentation is 2, which means I am going to divide this image into three segments, but the required one is 2. So instead of blindly using all local minima, I am going to manually set the seeds. Okay, this process is called over segmentation. The required one is 2, but I have 3 if you follow the watershed algorithm. Solution is we are manually going to set the seed location. So here we have 3 local minimum. I am going to take only the 2 minimum. So seed at pixel 3, seed at pixel 7. Now my basin is converted as 1, 2, 3, 4, 5, and basin 2 is considered as 6, 7, 8, 9. So the boundary would be somewhere between 5 and 6. Okay, I am omitting the pixel 5. So the remaining part would be one part, and the remaining part would be the another region. So without marker, we have three segments. With marker, we have two meaningful segments. So the first part represents the watershed algorithm, and the second part represents the um, seed marker based watershed algorithm. Okay, so the next concept is region splitting and region merging. Splitting, divisive clustering. Merging means agglomerative clustering. Splitting it is a top down approach, and agglomerative clustering is a bottom up approach. We'll start with the entire image and will recursively divide into smaller to more uniform subregions. The uniform subregions is determined based on the statistics. So we will use histograms to find the optimal threshold to determine the splitting regions. Okay, the entire image will be considered as one part. We will find the histogram of it, and if the histogram is below the threshold, I will split the regions into quadrants. The next concept in this divisive clustering is intra-region similarity and inter-region similarity. After dividing the region using the histogram, we are going to make the comparisons. So intra-region means we will compare within the same image. Inter-region means we'll compare with the different regions. So making the pixels within the region alike is known as the intra-region. Inter means I'll compare with other region, making the different regions to distinct. So if my nearest region is different, then then the split is right. If I have more similarity within my region, then the split is also right. So I will check both intra-region similarity as well as inter-region similarity. Intra-region similarity means the same region should have more similarity. Inter-region dissimilarity means the neighboring region should have dissimilarities. Then only I can say both the regions are different, then the boundary division is correct. Region merging means agglomerative clustering. It is a bottom-up approach. We'll begin with the individual pixels and will iteratively combine them into the larger one because we are merging it, right? So we'll use the boundary information to determine how to merge it. If there are weak boundaries, then it will be merged. If there is a strong boundary means then both the regions are different. So the concept of data clustering is also used. The if we have closest points in the region means then it is a single link clustering. If we have farthest points means then it is a complete link clustering. Then graph based segmentation, we will map the region pixels into the graphs. So assume we have a particular region, The internal difference of region R means this is your entire image, and we have divided the region R here. So here we will have pixels, so and so pixels here. All the pixels are considered as a nodes, and the connecting the node is called as a edges. So we will have a graph now. So all the pixels are considered as nodes, and all the connecting nodes are known as edges. We will draw the minimum spanning tree out of this. We will draw the minimum spanning tree to find the low weight among this. Okay, so the internal difference of R is nothing but we will find the minimum spanning tree based on the edge weights. So this measures the dissimilarity, maximum dissimilarity of edge weight within the region. A low internal difference suggests that it is a uniform region. If we have high internal difference, then it is not a uniform region, then we have to split the region again. Then the difference between two region, now we have looked only into the one region. Similarly, I have to take region 1 as well as region 2. I can find the minimum spanning tree internal R, and here also I'll find the minimum spanning tree, and I'll find the internal difference for R2. I'll take both the differences. So here I'm going to take minimum of both R1 as well as R2 based on the edge weights. If the difference is small, then the regions are similar. If the regions are not small, then the regions are different. So if the regions are similar means I can merge them. Okay, the merging criterion is, so we found the separate difference in an internal region, which means after finding the internal difference of region R, I can come to the conclusion that whether the similarities are in the same region. So after combining the differences means I can identify the similarities between the regions. So assume only one concept: in a particular region all the points should be similar. If you compare with the neighbor region, the points should be dissimilar. Then only the boundaries are distinct to divide the images. So when we need to combine the image means merging criterion is difference of R1 and R2 is less than minimum internal difference of R1 and R2. We have a formula for minimum internal difference of R1 and R2, which is min of internal difference of R1 plus regional penalty term of R1 and internal difference of R2 plus regional penalty term. So the tau R is given as K by determinant of R. I will show you an example, you will get better understanding. So I'm going to take a region R1 as 50, 52, 53 and region R2 is 54, 55. And internal difference, we'll find the difference. So we'll use minimum spanning tree to identify the difference. So for simplicity, I have directly taken the result. So R1 as the maximum difference among the pixels is 3. In R2, the maximum difference among the pixels is 1. So first part is over. Now we need to find the difference between both the regions. In this case, we have found only the internal difference, maximum difference. Next, we have to identify the difference between R1 and R2. So determine the closest boundary pixels. So difference here is 1. Now the tau R can be determined by K divided by determinant of R. K is a constant parameter and R is the size of the region. For simplicity, I am going to take 1 for now simple calculation. So now substitute in this formula, M int is internal of R1 plus tau R1, comma internal of R2 plus tau R2. So the 3 plus 1 and 1 plus 1 is substituted here. So minimum of 4 comma 2 is 2. And we already found the difference as 1. So 1 is less than this condition. So I can merge both the regions. So this is one part of image. This is another part of image. On applying the so and so condition, if the condition is true, then both the regions are similar. I have to merge into a single one. If the condition is not true, then both the regions are completely dissimilar. The first part represents some other color, second part represents some other color. So I can't merge them because they both are completely different. If merging them means it will produce a blended results. So based on this, we can perform merging also. Then the probabilistic aggregation. Probabilistic aggregation uses similarity cues. We have two main similarity cues. One is gray level symmetry, another one is texture symmetry. In gray level symmetry, we will find the minimum average intensity difference using this formula, as well as we will find the average intensity difference across the boundaries. So based on both the values, a lower value suggests more uniform transition between two regions. Then this texture similarity. Texture means if you take a human image, the human eyebrows, eye, nose, mouth are known as a textures. So we have to find the edges using the Sobel filter, and we have to plot a histogram, and based on the differences between histogram we are going to compare the similarities. So this capture how similar the textures are between the region. So now we are going to combine both the gray level as well as texture level similarity into a probability. So probability of Pij that represents the region Ri and Rj. The high probability indicates that the regions are very likely to belong together. So I can merge both them. If not, I cannot merge it. So that's all about split and merge. Thank you.